Hello and welcome. Today we're diving into one of the most ambitious engineering projects on the planet, ITER, the international collaboration aiming to replicate the sun's energy here on Earth through nuclear fusion. At the core of this immense challenge lies an equally immense piece of hardware, the ITER Tokamak superconducting magnet system. Let's explore the incredible engineering behind these giants. Imagine trying to contain something heated to 150 million degrees Celsius. 10 times hotter than the sun's core. That's the job of ITER's magnets. This isn't just any magnet system. It's the largest and most complex ever built, weighing around 10,000 tons and storing an enormous 51 gigajoules of energy. Its purpose? To create a powerful, invisible magnetic cage to confine and control the superheated plasma where fusion happens. There are several types of magnets working together. The central solenoid, or CS, acts like the heart, inducing the crucial electric current in the plasma. 18 massive D-shaped toroidal field, or TF coils, wrap around the plasma chamber, keeping the particles contained. 6 poloidal field, or PF, coils outside the main structure control the plasma's shape and stability. Finally, smaller correction coils fine-tune the magnetic field. To generate the intense magnetic fields needed, these aren't ordinary magnets. They use superconducting materials like niobium tin and niobium titanium, which lose all electrical resistance, but only when cooled to incredibly low temperatures, about -269 degrees Celsius, close to absolute zero. This requires a massive cryogenic plant circulating supercritical helium. Building such a system requires huge leaps in engineering, and recently, significant milestones have been reached. A major one is the completion of all major components for the powerful pulsed superconducting magnet system. This includes the final module of the central solenoid, built in the US and finished around April 2025. The central solenoid itself is staggering. Fully assembled from its 6 modules, each weighing over 100 tons, it stands 18 meters tall and creates forces strong enough to lift an aircraft carrier. Completing all modules caps over a decade of work. Just as vital is its complex support structure, an exoskeleton of over 9,000 parts designed to withstand immense forces. Production of the 18 giant toroidal field coils, shared between Europe and Japan, also pushed manufacturing boundaries. Each is about 17 meters tall and weighs over 300 tons, the largest niobium tin magnets ever made. This required a global ramp-up in producing advanced superconducting wire, over 100,000 kilometers worth. The large poloidal field ring coils, some up to 25 meters wide, have been delivered by Europe, Russia, and China. The installation of the first PF coil back in 2021 actually kicked off the magnet system assembly phase. Building these components meant overcoming huge hurdles, manufacturing building-sized parts with sub-millimeter precision, designing structures for incredible forces, developing industrial-scale production of advanced materials, managing extreme cryogenics, and coordinating it all across dozens of countries. As of early 2025, assembly is moving forward. 4 central solenoid modules were installed by January, with the 5th arriving in April. The final module is expected soon. Encouragingly, a massive vacuum vessel sector was also inserted into the Tokamak pit ahead of schedule in April 2025. The completion and ongoing assembly of ITER's superconducting magnets mark a triumph of engineering and global collaboration. These massive, intricate components are paving the way for harnessing fusion power, a clean, safe, and potentially limitless energy source for the future. It's a long road, but these engineering marvels bring us critical steps closer. Thanks for tuning in.